So if you have your slides available, you might want to go ahead and pull those up. Otherwise, just follow with me. And like I said, since you'll have this recording, you can get back to it when you need it. So chapter 8 is going to be dealing with stress and strain. And so that's your beginning chapter section, starting to talk about that concept. And it is the introduction to strength and materials. So this stuff is important because it really sets the foundation for everything you do from this point on. So it's kind of like solving reactions and statics. You got to know how to do that for just about everything. The stress and strain component that we'll get into here is germane to everything else you'll get into. So we're going to talk about types of stress, and the one we're going to look at is what's called direct stress. And then we'll look at strain, which is another engineering concept. And then looking at these two together, we can talk about this guy called a modulus of elasticity. And then ultimately we'll talk about tension testing and stress strain diagrams. And normally we would do a stress strain test or a tension test, but our machine is down because it's in the old building. So this would be our second lab we're going to do. I'm just going to give you data associated with this. And I have a couple of videos out there you can watch about that. So we'll talk about that next week, actually, more. And then the last thing we'll do in this chapter is Poisson's ratio. And if I don't get into that today, I'm not going to worry about it because we can pick up on that next week. Because I do want to do some problems with you primarily today. So that's kind of where we're headed. So let's take a look at this. So as we get into this, we've already dealt with statics. So we know the previous chapters dealt with that. And primarily the fundamental concept of statics was just looking at forces and how forces affect or act or react on your rigid bodies. So we also talk about that concept of a rigid body. Rigid body, of course, meaning that the body doesn't deform in any way, shape, or bend, or any of that kind of stuff. Because we're just looking at forces throughout that whole thing. And we're just looking to yield typically reactions using that concept of equilibrium. So what we're going to be looking at in this next section, chapter 8, is to look at strength of materials. So now we're going to begin to bring the materials into the equation. We're going to talk about things about modulus of elasticity and how that impacts it. So we will start to talk about concrete versus steel versus wood, as opposed to statics, which we really didn't care, because a rigid body was just a rigid body no matter what it was made of. So strength of materials then is the study of how internal reactions happen within the body from externally applied forces. So what's going to happen is when you apply a force to any kind of material, it's going to react internally. And that's the focus of what we get into here. And you can actually look at it more to macro level and a micro level. And we're going to look kind of at the macro level of how this body reacts internally. But if you look at micro level, then you get into the atomic structure, and you get into the molecules and how they react, which is completely different kind of concept. And that's usually a different course. In a 4-year program, you take a course called NAPALM, which is Nature and Property of Materials. And that's when it gets into the subatomic realm or the atomic realm. But this is more above that. And so this is what you're seeing in strength of materials. So when we look at this internal reaction, the body, you're going to include changes in the internal structure of the body. And we get into this concept of stress, strain, and deformation. And these are going to be really key to what's happening to the internal changes of that body. So stress is just kind of like what we think of when we have a lot of, like I have a lot of stress right now because I got a lot going on in my life. So the way I react to that is my stress level. And strain is usually talking about a deformation. Okay, so strain is how that body reacts to that stress in terms of it may elongate or it may compress. So we're kind of talking about that. So those are the two big areas we'll be looking at today. So when you think about this now, if you're properly designing a structure and or a member within that, the designer has to know more than just how the loads are running through it. So like our truss analysis, we were able to determine not only the reactions, but what was happening at each and every member or within each and every member in terms of the loading, whether it was compression or tension, and also what that value was. But from a design standpoint, we have to know a bit more about what's going on and how those members are also going to react internally. So we have to understand how the members will behave when loaded. So we need to look at things like how much will it lengthen or shorten, because if it lengthens or shortens too much, obviously that could be a problem. It could even cause failure. How much will it deflect or bend? If you load a beam and it deflects too much, then of course it fails. Or you may have things like ceiling cracks that develop because there's deflection going on. Temperature changes can cause problems internally. So we get things called expansion or contraction due to temperature ranges and changes. And any bridge that you drive over of any size typically has an expansion joint on one or both ends of it, where it allows your bridge to expand or contract with various conditions of temperature. So if you don't let that happen, you can actually have things get too compressed. Pavement on a hot summer day can actually explode if it doesn't have expansion joints, because the two sections will come together and basically just compress it until it can no longer handle it. So these are the things that we're looking at, and these are the things that the designer needs besides the loading and the load schemes. Okay. So let's look at types of direct stress. A very important concept here that we're going to get into. So the most basic concept is strength materials, and under strength materials concept is that concept of stress. And so as we think of stress, it is the internal resistance of a body to an applied force. So here's the one thing that you need to think about very, very definitely right now. Stress, it's an internal resistance of a body to an applied force, but it is in and of itself not a force. Okay, so a lot of people try to make it or think of it as a force, but it's actually not a force. It's just the way the body feels or reacts to that applied force. So what it does is it develops stress to keep your body from breaking apart to an internally applied force. And it can be viewed also as spreading out the total force over the resisting area. Here's a good way of thinking of that. If you think about a rope that has strands in it, when you pull with so many pounds on that rope, each little strand is going to be responsible for taking a little bit of that load, so it kind of bleeds that off. So area is going to be a big piece of stress because it's going to be completely related to how you solve that stress. And so for two different materials, well, not even materials, but two different sections that have different areas, if they have the same force on them, you're going to have a higher internal stress in one than the other, depending on what the area is, as we'll see here in a second. So the formula for calculating stress is very, very simple. It's related as sigma, which is stress, is equal to P, which is your force, divided by the cross-sectional area. Okay, so stress is usually that little sigma, and it comes in units of PSI, that would be pounds per square inch, or KSI, kips per square inch. Those are two typically ones that are used in the imperial system. In the metric system, we use what's called a Pascal, or the other way of notating a Pascal is what's called a Newton per meter squared. So you're going to have to pay attention to this one, because when we talk about this guy, it's usually rated in pascals or newtons per meter squared, and you're going to have to do a lot of conversion on that when you get into that. So conversions are going to be pretty important. Your force, your externally applied load P, is obviously going to be in units of forces, so pounds, kips, or if you are in the metric system, it's going to be newtons or kilonewtons, meganewtons, those kind of things. And then of course area, that's your resisting area, and that's going to be in units of linear distance squared. So inches squared, feet squared, meters squared, millimeters squared. And that's going to be important too, because you have to have a unit match between your between what you're going on to here. So we'll take a look at that. But so here's the major equation. Basically just your stress is equal to your force divided by your cross-sectional area. Now there are different ways of looking at stress. So there's different types of stress that can develop in a body, and it has to do with the way the force is directed and the resisting area that you're dealing with. Okay, so the most common one, and the one we're going to look at the most in this book, is what's called normal stress, sometimes called simple stress, or we might call it tensile or compressive stress. So in this case, the stress is developing parallel with the force, but the cross-sectional area is perpendicular to the direction of the force. Okay, so it's perpendicular to the direction of the force, and there's some pretty good books in there, or pictures. I'm going to draw a couple of pictures of these so you can see this. Then the shearing stress, the stress develops parallel with the force essentially. And what happens in this, the area of resistance is also parallel with the force that's being applied. Bearing stress is kind of a ripping type of thing where you have something trying to pull something out. So like if you have to drill a hole in a part, you put a bolt there and you pull that plate, that bolt, if it stays intact, it might try to rip a piece out of it. That's what we call a bearing stress. And then you have more complex types of stress, bending and torsional. So bending and torsional are not going to be considered in this course. In another type of course at higher college, you might actually go into bending and torsional stresses. Primarily in this chapter, by the way, it's just going to be your simple or normal stress and then your shear stresses. I don't even think we're going to look at bearing stresses. Okay, so these are also typically called, the tensile and the compressive stresses are typically called axial stresses. And so the stress will act in the direction of the applied load, and it's typically along the longitudinal axis. So let me see if I can draw you a picture here real quick. Go to the screen. All right, so show my taskbar. Okay, so in this case, let's look at what we've got here. If we have, there's a part that we're dealing with, and we're putting an applied load on this. So if I'm applying a load this direction, in this direction, so this is a force, and this is a force. So notice the force is axial with this, okay? And you could see that we are putting this in tension, so we would be dealing with a tension stress. So if I cut a cross section here and look at that area, let's say this is a rod, then what I'm getting is a cross section that would look like this. So this represents the resisting area of what this is doing, and so the stress is developing along this thing right here. So this is my stress direction. Okay, so this is the resisting cross-sectional area of that. So this would be called axial stress, sometimes referred to as normal stress. But I want you to note the area of resistance right here is perpendicular to the direction that the force is. Okay, everybody understand that? That's really, really important. We good with that? So let's try another type of stress. So let's say, oops, do that. So let's look at this type of stress. So let's say we got something here. Now I'm going to say these are connected. So let me see if I can erase this so you can see that there's these, let's say, are a part that's connected, okay? But that's kind of like a plane that exists between them. So assume that these are rigidly connected. So if you have a force right here that's pushing down, and of course that would be to equilibrium, you would also have to have the same force here. So what's happening is this thing is trying to push this so that it shears it off, okay? The area of resistance is right here. So this is your area. Now, of course, if we were looking at three-dimensional, that's coming out towards us. So this is my area. And that area is, notice it's now parallel with this force. So this is what's referred to as a shear stress that would develop in here to keep this thing from shearing off, okay? So the direction of that stress is developing, it's developing parallel with it like that. Another example of this might be of a shear stress, which you're going to see. Let's see, we've got a plate right here and another plate right here. And we actually have a bolt that we put through, let's say, that just represents my bolt, okay? So what we have is if we have a force that's running this way and one running this way, it's going to tend to want to rip that apart right here. It's going to want to shear that bolt off. So the cross-sectional area right here would be the area that you're looking at in shear. Okay, so again, it's the area that's resisting that force is parallel to the direction of the force, where in the normal stress, it's perpendicular. Now, we could look at a shear in the plate here, or not a shear, but a stress in the plate here and a stress in the plate here. So you could have a normal stress develop here and a shear stress develop here and a normal stress here. So in all cases, it's really a pretty simple process. If you have two plates, if I had a plate here and a plate down here, let's take a look at, draw my other plate here. If I have another plate sitting here, now this bolt has two areas of resistance right here and right here. And this is what we call double shear. So we have what's called a shingle shear and a double shear. We're going to take a look at examples of these problems here in a sec. Okay. So it's actually pretty easy because the beauty is you use the same equation for all of these. Now let me show you one more type of shear, which your book doesn't talk about too much, but I just want to bring it up because it's kind of, you'll see this one as well. So if we look at this one, I'm going to draw two diagrams here. One is looking down. Actually, I just do it on. So let's say we got a plate and we're looking down on this plate and we have a hole in this. So we put a bolt right there. And if we pull this plate, this way with a force, and of course that's going to be pulled that way. So this is rigidly attached. What's going to happen, it's going to want to try to fail right here. Pull that piece out. That's called a bearing failure right there. So it would want to rip that out. So the area that you're dealing with is the area right from here to here. Okay. So this is what we call a bearing type of shear. And there are no problems in your book that deal with bearing shear. So the good news, we really only have to look at two types of stress. We have to look at I'm sorry, that was bearing stress, not bearing shear. We have to look at bearing, or we have to look at normal stress, which either is what they call axial or tensile. And then we have the other type, which is called a shear stress. Okay, so let's go back to the diagrams. Okay, so axial stress usually is either in tension or compression. So we can talk about tensile stress or compressive stress, but we can just use the general term axial stress. Sometimes we also call it normal stress because that refers to the fact that the area of resistance is perpendicular to the direction of force. Okay, so stresses will act in the direction of the applied load, typically along the longitudinal axis. That's why it's called axial. Shear stress is that one that's going to act parallel to the applied load. And the area is also parallel with the applied load. And the bending and torsional, they're more complex and we're not going to consider those, okay? So it's very, very important to understand the difference between stress and force and also understand that, again, I'm going to emphasize this now and keep saying that throughout, is that stress is not a force, okay? It is an internal resistance to that force, all right? So it's an internal reaction, and to calculate it, it's just using that cross-section. Now, one thing to understand, we'll come up with a number when we calculate the direct stress, but that's just an average across the cross-section. So if you think about it, and this should make sense, where the point of application of that load is actually happening, the stress may be higher at the point of the load contact than as opposed to, let's say, the edges of the area. But we just calculate the average across the board, and that's what they're using. So when you see a stress number or calculation, it's actually an average stress across the cross-section. It's not an actual stress in terms of that. Now, depending on what you're doing, you might need to know some of that stuff, but we don't for our purposes. So everything we're going to deal with is going to be pretty straightforward. So want to look at a couple of examples with you, a couple out of the book and a couple that are not out of the book. So if you have your book, you can follow along. I'm going to start with 8.2 or 8.1 rather. And 8.1 gives you two simple cases. You've got a bar that has two different types of cross sections on it. And let me go over to my screen here. And you'll see the math on this is really simple. This is actually probably easier than some of the stuff that you'll do in other things, especially like we got done with the trusses. Let me just go ahead and we'll clean this up. I'm going to draw this picture real quick. Give me a sec. Okay, so we have a bar that has two components to it. One kind of, whoops, that's not a bar. We have a bar that looks like, let's say this, and another, this is connected to it. Okay, so this is a bar that has, you can think of that as one continuous material. Draw that out of there. It's connected like that. Okay, and we're going to look at two cross sections on this. One cross section here. And then we're going to have another cross section over here. So we're going to call this cross section BB. And this is section AA. Let me clean up some of this other clutter I got in here too. So we also know that the cross section for section AA is given, the area is 4 square inches. I'm sorry, that's for BB. The area for AA is 2 square inches. So that could be, this could be 2 inches by 1 inch coming at us, and this could be 4 inches by 1 inch coming at us. That's where these numbers are coming from. Now, sometimes you're going to have to calculate those numbers, so it just depends on what's given in the problem. So this one's pretty basic. So just keep in mind, this is one continuous bar, a homogeneous material, and it's got a load going like this. So let's say we've got 4 kips in this direction, and for equilibrium, we got 4 kips in this direction. So because the sizes are changing, we're going to see different stress levels in this. So if we solve the stress for section AA first, that's just simply equal to force divided by the cross-sectional area. And remember, the cross-sectional area is perpendicular to the direction of force. So the force is 4 kips. We're going to divide that by 2 square inches. And so we get a value of, you could call it 2 KSI. But if you're in terms of pounds, that would be 2,000 PSI. Okay, everybody see how simple that is? Any questions on that?
No.
So if we look at the stress level here, now keep in mind, this is the same bar, but because the cross section has changed, the stress level or the stress developed at BB, again, is force divided by the cross sectional area. So the force in this case is still 4 kips, but now we're dividing it by 4 inches squared. So this would give us 1 KSI of stress, which could also be considered 1,000 PSI. So notice what's happening because the area has changed drastically in half, the stress level is going up. So in other words, if you can bleed that stress or that force out over a larger area, what you can do is decrease the stress level. So what is the limiting piece of the material here at section AA or section BB? Which is more limiting? Anybody know? Which has the higher stress level, section AA or section BB? Obviously this one, right? So this could be a limiting factor to the point where when you're designing this, if this exceeds a certain maximum, you may have to increase the area of this to make that work, okay? We'll have a lot more to say about that later. All right, so let's take a look at a second problem. And this is the second problem that's dealing with this. It's problem 8.2, and they show you a column that is sitting on a footer, and they're going to have you calculate different stress levels. So let me go ahead and I'm just going to erase this whole thing. All right, so we're going to look at, we got a column that is sitting, your book has a picture like a three-dimensional column, but I'm not going to be able to draw it three-dimensionally, so I'm just going to kind of do it like this. That's supposed to be sitting on that. Let me see if I can redraw that.
Which problem is this?
This is 8.2. They show it a little bit different. He shows it three-dimensionally, Max. Oh, geez, okay. Let me try that again. Yeah, the first one I did was 8.1. There we go. That's a little bit easier to do it that way. Okay. So you have, I believe this is like, let's assume it's concrete. The fact is it really doesn't matter what material it is at this point. We will get into materials here in a bit. So we got a load on this of 20 kilonewtons. So this one's going to be metric, and you're going to see units are a little bit more important. Well, they're always important, but we know that this is 1.5 meters, and this will be square. So it's going to be 1.5 meters this way by 1.5 meters coming at you. Okay, does everybody get the idea? And this guy is 5 meters high. And we also know that this has a cross section here of 250 millimeters squared. Okay, so I'm already giving you the square millimeters on that. So if we want to calculate the stress developed in this column, and we want to calculate the stress developed in this footer here. So we're going to have a cross section coming through right here. And actually we could put it anywhere. We're going to call this section AA. And I want to look at what's happening down here in the footer. And this is BB. Now, you kind of understand what footers are about, really. If you're whole loading with 20 kilonewtons here, what it's doing when it gets down here is it spreads it out. And what we're going to also see is that the stress up here is going to be a lot higher than the stresses down here because it's spreading it out. Okay. So here's the other thing, too, that we have to think about, is that we are now dealing with metric, so we've got a lot more conversions we got to look at. So this is in millimeters. Typically, you probably want to be in meters. So the first thing I want to do is convert a millimeter to, actually, let me back up a minute. This isn't actually millimeters squared, it's just 250 millimeters, but it's a square section. Okay, so you make sure you change that because we're going to change this here. Okay, so it's actually just 250 millimeters by 250. Sorry about that. Okay, so the first thing we're going to do is convert millimeters to meters. So how do we convert millimeters to meters? You can tell me. How many millimeters in a meter? Anybody know? Nobody knows that?
1,000.
1,000, right. So we're going to take 250 divided by 1,000. So this gives me actually what? 0.25 meters, correct? So the area at AA is going to be 0.25 squared. So that gives me 0.0625 meters squared, okay? All right, so to get the stress at A, it's going to be the force divided by the cross-sectional area. So the force is 25 kilonewtons divided by 0.0625 meters squared. So we have 20 kilonewtons. That gives me, what'd you guys get? 320? Anybody get that number?
Yeah, that's what I got.
So what the unit of this would be kilonewtons per meter squared. Another way of referencing a kilonewton per meter squared or a newton per meter squared is what's called a Pascal. So you could also call this a kilopascal. So these are exactly the same. So you got to watch that when you get into metric, okay? Metrics are a little trickier because it's a real big unit game, okay? So let's look at section BB here now. So we know that the area for section BB is already in meters. So since this is a square cross section, we're just going to square that. That gives me 2.25 meters squared. You guys agree with that number? That's already in meters. And I told you initially this was 1.5 this way by 1.5 coming towards us. So to get the stress at section B, it's again force divided by cross-sectional area. And notice because the area perpendicular to that force is bigger now, we should notice a reduction in the size of the stress. So we have 20, again, kilonewtons divided by 2.25 meters squared. So we have 20 divided by 2.25. That gives me basically 8.89 kilonewton meters squared, which you would typically just call kilopascals. Okay, so notice the reduction here is quite a bit, a lot higher in the column than it is in the base, which is your footer. Notice also on this problem, this 5 had nothing to do with anything, so it didn't matter really where we took the cross section. Okay, and also again, I want you to understand that the stress is calculated across this area as the average stress, because it actually could be higher here than it is at the edges. Same thing here. It's probably a lot higher here than it is at the edges, but we're looking at that as just across the board. Is everybody okay with that?
Yeah, seems pretty easy.
It actually is, although it's a big units issue, okay? Units are really extremely important. And especially when you get into the metric, they're a little trickier, okay? So you got to watch that. Just remember that 1 Newton, here's your equation, 1 Newton per meter squared is the same thing as 1 Pascal, okay? So we're going to use that a lot. All right, so let's go back and we'll take a look at some shear stress. Now shear gets a little bit more involved, but it's not that much different. Okay, so that other type of stress we want to consider is shear stress. So when you think about shearing, it's the ripping apart kind of concept that's trying to happen. So shear is trying to rip apart that body. It's trying to rip it like a bolt. It's trying to shear that bolt apart. And it's very much calculated like a tensile and compressive stress. You use the exact same equation. It's still a force divided by cross-sectional area. The only difference here is that our shear stress develops parallel to the direction of the applied force, and the area is also parallel to that direction of the applied force. So it's different from that standpoint, okay? So let's take a look at a couple of examples, okay? So I'm going to look at, I'm trying to not use exactly the same ones that are in your book, but I'm going to use for the first one, I'm going to use problem 8.3 so that you'll be able to look at this later on. I'm not going to be able to draw this picture exact, so but let me give me a sec here. We'll try to do this as best we can. I was really dooming this morning. I could not get this thing to work, and I finally had to reboot right before. This would not have been good if I wouldn't have had this thing. Okay, so in this case, we have a plate that is bolted, two plates actually that are bolted together. So I'm going to have to draw two kind of cross sections here. I'll try to do the best I can. So you got one plate, let's say here, and another plate here. Let's see. Like this. And you have 4 bolts in this thing, so we're looking at it from the side, so you really only have one bolt here from the side and another bolt here from the side. So these are usually put in some kind of bolt pattern. Now if we look at this from the top, what we've got, I'm going to try to draw this so that we can see this direct. It's hard for me to get circles in here, so I'm going to try to do the best I can. So this is the plate. One plate's on top of the other, but what's happening here is we've got, because the one's on top of the other, you wouldn't see this line. It would be what you would call a hidden line beneath, okay? And we're going to have a force coming this way and a force coming this way. So this force is related to us as 15 kips. 15 kips. Now in this picture, I'm going to try to do the best I can on this, guys. I think if you follow the book, you'll see a little bit better picture. But I have a bolt here, and a bolt here, and a bolt here. Those are pretty much ovals. Okay, recognize those being in the same direction. Okay, it's all together in a group. So we also know a couple of other things. We have the plates. There's actually, let me see something in a minute. There's actually a plate thickness given here. Give me a sec. So we have this plate thickness here, this plate thickness, and this plate thickness is, let's see, that's 1/2 of an inch. And this guy is 8 inches this way. So this is 8 inches. Each bolt, really lousy looking bolts, but each bolt is a 1/2 inch diameter. Okay, so we have 4 bolts, 1/2 inch diameter. And let's do this. I don't think this problem's doing this, but I'm just going to show you something a little bit different here. So let's say that this is 1/8 of an inch thick. Okay, so we're going to look at that. So what we're going to do is calculate the area, and then we're going to look at that in terms of how we would do different types of shears or different types of stresses. So I want to look at the stress that's developed right here. This is called your shear plane. That's your shear plane, okay? So we have to calculate the area here. So we have an area for each bolt, and then we have 4 bolts. So the first thing we're going to do is calculate the area of a bolt. And that's going to be equal to pi d squared over 4, okay? D being the diameter. So what we would have is pi d squared is 1/2 inch over 4. If you're not familiar with that equation, you're going to want to learn that equation because you're going to be utilizing that a lot. So instead of pi r squared, we're using pi d squared over 4. So one using the area, one using the radius. Very often in strength problems, you know the diameter more than you do the radius. Okay, so we're going to take the 0.5 and square it times pi divided by 4. I came up with 0.1963, and this would be inches squared. Does everybody agree with that? Anybody get a different value?
Nope.
Okay, so this area of resistance is just at 1 bolt, but we have how many bolts here? We have 4, right? So the area total of resistance is going to be your area of a bolt times the number of bolts. In this case, we have 4. So if you have 8 bolts, it would be 8 times that. You had 3 bolts, it would be 3 times that. So you just got to look at the number of bolts that you have and how that's resisting. So that's my total area of resistance. So the shear stress, S for shear, is still force divided by cross-sectional area. So the force is 15 kips divided by my total area of resistance, and those bolts I came up with 19.1 KSI, which if you put that in PSI, you would multiply that by 1,000. You could also express that as so either way, 19.1 KSA or 19,100 PSI, okay? So that's what we call a single shear problem. And if we looked at the plates now, we could look at the plates and see what the shear or the amount of stress in the plates is. So this is no longer a shear problem. This would be a normal shear. So for this plate, let's call this plate X and this plate Y. So for X, the area at X would be 1/2 times the width of 8. So that would give me 4 square inches. So the stress, which would be a normal stress at plate X, would be the force 15 kips divided by 4. That gives me 3.75 KSI. And for the plate, for plate Y, the area is 1/8 of an inch times 8 inches. That's 1 square inch. And the stress at plate Y is 15 divided by 1. So that's 15 KSI. So what we have, notice, is the shear in the bolts is the highest amount of stress. Okay? So basically what this is essentially saying is this would tend to probably fail first, that could fail secondly, and that would fail third. And if you put what's called an allowable stress into that equation, then that can be a problem. So this is, what I did was an example. This is an example of a shear stress right here, okay? Where this is an example of a normal stress. I kind of did both things with you on that one. You guys get any idea? Anybody questions? No questions? All right, let's try one more here. We're going to look at the next problem, which is 8.4. And this is a double shear problem. So this is a little different. Let me draw this a minute. So we got a plate and another plate. So here's what we've got going on here. And we have a group of bolt pattern, a bolt pattern that's kind of like that. So if we're looking at this from top down, we're looking at me. Try to do that a little bit better. Line those up. And we would have that guy right there. That represents the plate coming out. So this would be hidden. You couldn't see that. Now we have 3 bolts in this one. I wish I could draw circles better with this. So there's a bolt here. Whoops. Bolt here, and a bolt here. Well, I think you get the idea. All right, so those should be right in a row. That's not a very good picture, but that's what's going on. So again, we have a 1/2-inch plate here, 1/2-inch plate, and these are a 1/4-inch plate, I believe. This is a 1/4-inch plate. This bolt is got a diameter on it. They're 3/4 inches diameter. So we're pulling with 50,000 pounds. So this is going to split. Each one of these is going to take half of that. So you got 25,000 pounds in each. That's 25,000 pounds. So in this problem, you have 2 shear planes, one here and one here. So this is what we call a double shear problem. So those are really going to give you 2 areas of resistance. Okay. So you got ways you can handle this. The first thing is to calculate the area. And so what I'm going to do is calculate the area for a bolt. And that's going to be pi d squared over 4. So what we have is pi, diameter is 3/4 squared over 4. So 3/4 squared times pi divided by 4. I get that's, let me see, 0.785 inches squared. You guys agree with that number? Anybody questioning that?
So the 3/4, why?
That's up here, Jacob. That's the diameter. That's the diameter of the bolt.
Okay.
So D represents diameter in this equation. Okay.
Okay.
So now you guys are normally used to using this equation for a circle, pi r squared, right?
Yep.
But if you took that and divided it by 2 and squared it and multiplied it by pi, you're going to get the same numbers you get here.
Okay.
And in strength of materials, you're going to see diameter given much more than you will area, okay? But you should be able to do it either way, okay? Either way you're comfortable with. But we're going to be utilizing this equation a whole lot more because, like I said, in strength of materials problems, you usually know the diameter of a rod or you know the diameter of a bolt or something like that as opposed to its radius, okay? Does that make sense?
Yeah.
So here's the other thing you got to really think about. How many bolts do we have?
3.
We have 3. So we want the area total. So we're going to take the area of a bolt times the number of bolts times the number of shear planes. So in this case, we have 2 shear planes here, right? So we have area of bolt times the number of bolts times the number of shear planes. And that's going to be our total area of resistance. So we have, let's see, let me check my number a minute. Whoa, did you guys get that number? Let me check something real quick. I don't have this number. Did you guys get this number by any chance?
What number?
That's 0.785. Check that number. I don't think that's right. I just checked mine. I think I keyed it in my calculator wrong.
I got 0.44.
All right, that's what I did too. All right, so we need to change that. I just checked that, Max. Sorry about that. I didn't think that looked right after I started looking at it. I gotta watch this calculator sometimes. And you know, you catch me if you're not getting what I'm getting. It's possible it's on my end, okay? So let me check this a minute. Is there, yeah, dang it. Getting different answers. 0.4402. Is that right?
Yeah.
Okay. All right, so we're going to multiply that times 2 and then times 3 because we get that amount of shear happening, or that's the area of resistance for the total amount of shear. Okay, so we have 2.65 inches squared total. Everybody agree with that? So the stress of shear is force divided by the resisting cross-sectional area. In this case, it's 50,000 pounds divided by 2.65. So you get like 18,000 something. 18,862. We call that 63 PSI. Everybody seen how that works?
Yep.
Anybody questions?
So what's that last number, that 18,000? That's figuring the...
That's the amount of stress that develops in these bolts essentially due to the shear force that's being pushed on them.
Okay.
So if there's something typically called an allowable, and I'm going to talk about that here in a second. So if you have what's called an allowable stress, that means if the stress exceeds this number, or this number exceeds the allowable, that means this has the potential to fail. Okay? So if you get a bolt that's 3/4 of an inch diameter, it may have what's called an allowable stress. So you might see an allowable stress on that, which they call an allowable. Let's say it's 20,000 PSI. So if we have a design right now that's got a design and it's got 18,008 PSI and the allowable is 20,000 PSI, are we failing the design or is the design okay? Think about that. If the allowable on those bolts is 20,000 PSI and currently we're coming up with 18,800, are we okay? Or are we in trouble of failing?
Should be okay.
We're okay. As long as this number is under the allowable, we're good. But now what's happening here is we're getting what? We're approaching that, right?
Yeah.
So we're getting to the edge where if you were designing this, you might want to consider doing something different. Does anybody know what you could do to make this number better? In other words, lower it?
I would say, yeah. Add another bolt, but if you're cutting into it and adding another hole, would it make it?
It might make it weaker, but
Yeah.
another way to do that is all you have to do is increase the area, right? If we increase the area, you decrease the stress. Do you see that? So one way of increasing the area would be to what? Step up the diameter on that bolt, right?
Yeah.
And that would drop it so that the allowable, we would be less than the allowable. So this is the kind of things that designers get into all the time. And you're going to see when we get into these problems in the book, there's going to be a little bit of that going on. Okay. So let's do another problem real quick, and I'm going to give you a little example showing this. So this is pretty simple. You guys okay with the shear stress before we move on though? Single shear, double shear. See how that works?
Yeah, we're gonna go over this more on Thursday too.
Absolutely, because you're going to have some problems to work. Okay. Yeah. So I'll give you some problems, and then yes, we'll definitely work on this on Thursday. Okay. Okay.
Yep.
So let me, we're going to do a little bit different problem. Okay. It's kind of similar. Now this will be a normal stress problem, or a direct stress, or axial if you want. So we have this really thin little rod right here. Okay. And we're going to say it's loaded right now like this. So that rod's in tension. And this tension force is 20,000 pounds, or 12,000, excuse me. And the rod diameter, the diameter of this rod is 1 1/8 of an inch diameter, okay? So we want to calculate the normal stress, okay? So, and this would be a tension stress, right? Because this rod is in tension. So first we need the area, and that would be pi d squared over 4. So let's see what we come up with. So that's going to be pi times 1.125 squared divided by 4. You guys check my number, okay? I don't trust this calculator. I get 0.994 square inches. You guys agreeing on that? Everybody okay with my area?
Hold on.
Okay.
Yeah, that's what I got.
That's good. Okay.
Yeah.
So to calculate the stress, and this would be a tensile stress, okay? So if we called that T for tension, it's just simply the force divided by the resistant cross-sectional area. So the area is in that section. So the force is 12,000 pounds, dividing it by the area. So our stress that's developed due to that so we're looking at 12,072 psi. Or you could call that 12.1 KSI. All right? No problem with that, right? Is that pretty good?
Yeah.
Yep.
Yeah.
Now let's look at another. We're going to put a little wrinkle in this. So what would be the case, let's say, if this rod has an allowable stress in tension? So the allowable stress in tension is actually 20,000 pounds due to the material. So this is the allowable. So what would be the maximum force that you could put on this rod before you would fail it? Or fail, you wouldn't necessarily fail the rod. In other words, you wouldn't necessarily break or rupture the rod, but our design would fail. So we want to see what's the maximum, and we want to see if this has already exceeded the maximum or not. So here's how we handle this problem. We're going to just use the stress equation, but we're going to say this time that the stress allowable is going to be equal to the force divided by the cross-sectional area. And in this case, what we're solving for is P, because we know the allowable and we know the area. So it simply becomes the area times the allowable. So the area is the 0.994 times an allowable 20,000 psi. So the maximum force that could be applied to this, 0.994 times, would be 19,000, basically 880 pounds. So if we exceeded that, if we exceeded this number, the potential for this rod to fail would be strong. And in tension, you may have a different allowable number in tension than in compression, depending on the material. So this would be what you would call P max, the maximum force that you could apply that rod to with tension before it would potentially fail. And these numbers are determined through codes. They might come up through building codes, or they might be experimentally derived, but this is nothing that you typically come up with. This is something that's given to you. Okay, you guys seeing how we did that now? That's a little twist on what we just did, and that's a lot of what you'll be dealing with when you're dealing with these kind of problems. Any questions?
Nope.
You get the idea? Are you getting the idea about the stress equation is the same whether you're talking about shear stress or bearing stress or any of those stresses, but the direction of the area with respect to the way the force is acting is different. Okay. And that's a lot of what you'll be dealing with in these problems. And of course, units. Units are going to be a big thing as you get into this. All right, are we okay on that then? Will we move on to the next concept?
Yeah.
Okay, so I'm going to, let me flip back here. I'm going to clean this screen up so that when we come back into it, because we're going to be doing another problem here, we'll be right where we need to be. All right, so
sorry about that. My computer died.
no problem, no problem. So take a look at these examples. We basically went through 3 and 4. I didn't do 5 with you, but you can check that one out. And we can take a look at that also on Thursday. We're going to have some time on Thursday for sure. Okay. Like I said, we only need about an hour, hour and a half to take that test. So shouldn't be a big deal. All right, so let's move on. So the next thing we want to take a look at is strain. So strain is another engineering kind of thing we talk about when we're talking about materials. And so due to the stress that is happening in an applied load, it's typically going to be accompanied by that body deforming. So what we're talking about deformation is if you're pulling it, that body is going to want to stretch. And if you're pushing on it, it's going to want to compress. And if it's stretching, it's also decreasing. Let's say if you're pulling on a rod, the cross section is actually necking down. So it actually happens. There's 2 kinds of deformation that are going on. One in the axial sense and one in the lateral sense. So the axial direction is usually more important because that's a bigger number. We usually don't even care about the one in the cross section. And the same thing happens if you push a rod, it's going to compress, but the cross-sectional area will increase a little bit, but again, it's really minimal. So deformation is the change in length that a body's going to undergo to a push or pull. So we're really going to be considering more of that than we will the other direction. Okay, so it's the axial direction. So what really happens is as you apply a force, either in compression or tension, your atomic planes of your body, they're beginning to slip past each other, and that slippage results in your change in length. Now, like I said, if you're taking a course in nature and property materials, you're really looking at those slip planes, and you're looking at that atomic arrangement. We're not looking at that at all. We're just looking at the small amount of incremental change that sometimes we can measure and sometimes we can't. So a lot of times, if your loads are small, there's a change going on in the size of that body, but we can't detect it. But if it's a large load, there is a change that is detectable, it's measurable. And so we're really considered more in that larger kind of issue here. So deformation is considered to be the total change in length of a body. And this is often expressed as a unit on a unit basis, or we might think that that's unitless. And that expression of deformation per unit length is referred to as strain. So basically, we're just comparing a length to a length. That's what it really is. It's a length to a length. And the deformation of strain for unit strain is simply strain, which is this epsilon, I believe, which is a delta divided by L. So what this is your length per length, where strain is in unit per unit. Deformation is the total amount of change in length, okay? So it might be in inches, it might be in millimeters, it might be in meters, and L is your original length, and those units are in inches, millimeters, and meters. So if we go back to this equation, what we're saying is this is the total amount of change. So it's either shortened by a certain amount or it's lengthened by a certain amount. That's what this number represents, divided by the original length. So if you had a rod that you pulled and the rod's length was originally 20 feet, and then you measured like 0.01 inches, this is the amount of change, the 0.01 inches is the amount of change. So it's just a length divided by a length. The incremental amount of change divided by the original. And this is what we call our strain. Usually we think of it as being unitless, but I'm going to show you you can have that in different values. So strain is best explained as the deformation that occurs over every unit length of the body. So in other words, there's an incremental little piece of change going on, either a elongating or a shortening, but the deformation is just the sum of those incremental changes. So when an axial load, such as tension or compression, is applied, strain is referred to as an axial strain. And when a deformation is caused by a shear stress, then that's called a shear strain. A lot of times we don't make the distinction, but just understand that sometimes we're talking about an axial strain if it's related to an axial stress, or a shear strain if it's related to a shear stress. So we're going to take a look at example, and one example here. This is a really easy concept. There's not much to this, but I'm going to show you two examples of how we do this. Okay, we're going to look at 8.6 right now, and then we'll pick up with some other concepts. Okay, so let me flip over here. Okay, so in this example, you're shown a column that has an original length on it. So let me draw this up. Now, we haven't talked about materials yet. We will get into materials. So we're still kind of talking material independent. But let's say we have a concrete footer. And on top of that, we placed a concrete column. So it's trying to spread that load out. And these guys are rigidly attached together. So essentially, you're not seeing any. Okay. So we have a force that we're applying on this P. We actually don't even know anything about the force in this example. It's just a force that we have. And we have some dimensions. Let me, we have a dimension here. And we have a dimension line here. We also have over here. Okay, so let me put some numbers here for you. I'm sure glad I was able to get this working. I was really dooming how I was going to even handle this, but something happened with my driver on this and I had to deal with that. So the original length on this column is 10 feet. And the amount of deformation due to the load is 1/10 of an inch, which is actually pretty much, well, not much, I guess, but so this is a concrete object. We know the original length, if we measured this, was 10 feet. We've loaded this with a force P, and because this is compression, this thing is actually going to be, due to the load, decreased by 1/10 of an inch. So notice the units here, we're inches here and feet here. So strain, quite literally, is defined, your strain is defined as your incremental amount of change divided by your original length. Well, in this case, our incremental deformation is that amount. That's in inches. L is in feet. Now, we can convert that to inches. If we multiply that by 12, that would give us 120 inches. Everybody agree with that number? I'm getting that? Just multiplying that by 12, right? So you've got two ways of speccing out strain. We can say that it is inch per inch. So in that case, it would be So the amount of strain right now then would be 0.1 divided by 120. And that would give us 0.00083. We would call that inches per inch. But another way of looking at that is that's unitless. Okay? So you can also define strain like this, where you're using inches and you're using feet. So in this case, you get a larger number. It means the same thing, but it's in a different unit. So in this case, you would say that your strain is inch per foot. I guess I might want to, maybe it's better to say this, inch per foot. These are saying exactly the same thing, but notice this is inch per inch and this is inch per foot. So what's important is making sure you recognize what your unit is. This is more common to do it this way, okay? So this is way more common than to do it this way. Because when you get into other problems, it's very important that you've got it in that unit. So when we define strain, we want to normally define strain as a unitless number. Okay, and we will keep it typically inch per inch or millimeter per millimeter or meter per meter, depending on what you're dealing with. Does everybody get the idea? The amount of deformation divided by the original length. So this would also, because this is compression, this would be considered a compressive strain. Okay, we don't also normally make that distinction too much, but that's that could be out there as an example. Okay, so strain's pretty simple. So far, wouldn't you agree that stress and strain are pretty simple? And notice we don't have to worry about cross-sectional area here or anything like that. And in fact, force didn't even come into play. Somebody already measured this for you, okay? Now there are going to be ways to determine this amount if you put a certain amount of P, and we're getting to that here in a minute. And also, I want you to understand at this point, we haven't even looked at materials, but that's coming. Okay, any questions so far?
Nope.
Okay,
No.
so let's go back. we're going to go to another concept now. So now we're going to put these two together. And this is a process of what's called the modulus of elasticity. So now we're going to begin to look at how stress and strain interrelate. So the relationship between stress and strain becomes one of the most important properties of a material. And each material is going to respond to force and stress and strain differently. So this becomes, modulus of elasticity becomes a signature or a property of that material. And one of the first people to kind of investigate this was a gentleman, scientist by the name of Robert Hooke. He began to recognize a relationship between load and deformation. Now, he was dealing with this in the 1600s, and the concept of stress and strain at that time did not exist. So what Hooke was doing, he wasn't using that concept of stress, which was force divided by cross-sectional area, and strain, which was length of deformation divided by total or original length. What he was looking at was taking a spring, and he would load that spring with a force, and so he was measuring force and the amount of elongation of the spring. So he was dealing directly with force and distance as opposed to stress and strain. But this early on became known as Hooke's law, and it's still a useful principle. So later on, Thomas Young came along, and he began to define this concept of stress and strain. And so he looked at the relationship of stress placed on a body and its subsequent strain. So this development occurred in the 1800s, like 200 years later. And he found that for materials, there was a constant property that occurred between each material. So in other words, steel had a certain value, and concrete had a certain value, and rubber had a certain value. So this became known as the modulus of elasticity, and it's sometimes even today referred to as Young's modulus. So you'll see that term interchangeably used. Most people now use the term modulus of elasticity. So the modulus of elasticity, and that's expressed as the uppercase E, is very simply just the comparison of the amount of stress divided by strain. So essentially, you're just graphing stress divided by strain, and it turns out to be a linear relationship. So modulus of elasticity will have the same units that stress is in. So it's going to be PSI, KSI, kilopascals, whatever. And we'll see why that is mathematically here in a minute. But if you're looking at stress is in units of PSI, KSI, whatever. And if we're looking at strain in inch per inch, this is unitless. So if you divide a number by a unitless value, you can notice up here again, if this has units of PSI and that has no unit, then this is going to be a unit of PSI as well. So the modulus of elasticity now gives you an engineer the ability to predict behavior of a material under values of stress or force. You can think of it that way too. So for most materials, your value of modulus is, modulus elasticity is a constant. Now that's not true for all materials, but most of the engineering materials that we would deal with, we consider it a constant value. So in other words, each material that you deal with has a property called a modulus of elasticity, and that's a constant value that we use. So that gives your designers the ability to determine deformation based on that under certain amounts of stress or load. And this is definitely an extraordinarily important tool for design. We really couldn't deal without it. These are average values that you can find for modulus of elasticity. These are experimentally derived by basically taking materials, loading them, measuring stress, measuring strain, and determining how this works. Okay, this is out of your book in chapter 8. This is table 8. If you look at that, it's on the top of page 256. So again, just keep in mind these are averaged values. You can also find a little bit more detail on these in Appendix B in your book. But you can also look these things up on the internet and whatever. And you can find them, they're typically expressed in PSI or megapascals. And notice, I just want you to look at some of these for steel. 29 times 10 to the 6th PSI. Steel varies depending on the amount of carbon that you have in it. So this can go anywhere from 28 times 10 to the 6th up to a max of 30 times 10 to the 6th. So the more carbon you put in it, the higher that number is going to be. Okay. Aluminum typically is 10 times 10 to the 6th, or notice it's 70 times 10 to the 3rd megapascal. And a mega is 10 to the 6th. So if you were looking at pascals, that would actually be 70 times 10 to the 9th. So we have to think about that. Brass, copper. Now timber is going to vary depending on the type of wood. So for instance, a southern yellow pine might be different than, let's say, a northern oak. Okay. So this is a really, really definitely averaged area or average PSI. And same thing with concrete. So concrete is going to vary also depending on your additives and your aggregate and the amount of different materials that you're putting into it. So those are some things to keep in mind, that those are just averaged. So what do these values actually mean? So by definition, your modulus of elasticity defines the stiffness, or what you might call the rigidity, that a particular material possesses. I actually like to think of modulus as the resistance to being pulled apart or something. So that stiffness is a resistance to that. So the higher the value of E, the more stiff or the more rigid the material is. So for instance, you take a rubber band, that's not very stiff. It's going to really, really pull. So what happens, you're going to have a really low number when you talk about its modulus of elasticity. But if you look at steel, 29 times 10 to the 6th, that's a much higher number. So it's got a lot of resistance to being pulled apart. So it's not going to be like a rubber band that you can just pull in and out. It's going to take a lot of force to make that thing change. Now, this is not necessarily a measure of strength, but many materials exhibit the fact that if they have high E values, they're going to be considered strong. So we very often will think that, okay, if it is a high modulus of elasticity, then we would consider this strong. Okay. So the other thing we're looking at too is you can think of those numbers as a slope, where if we graph the strain on the x-axis and the stress on the y-axis, we get the slope of that line. So that slope is really your E. I'm going to show you that, but we're going to look at a couple of examples here where we deal with this. So again, keep in mind what we're going to be utilizing is this equation back here. That's going to be important. That's stress divided by strain. And I'm going to show you kind of how that works here too in a sec. So also keep in mind on these numbers, notice steel is a really high. In other words, it has a really large slope as opposed to concrete, which just has a lower slope. So let's take a look at that. And let me see, I'm going the right way. No, going the wrong way. Okay, so we're gonna take a look at problem 8.7, and then we're gonna look at 8.8. Okay, so let me flip over to my other little whiteboard here. So this is where it's going to start to put all of these equations together, and you're going to see this is where it gets a little bit more involved than it has been, but I think you'll see it's not that big of a deal. So first off, let me start out by looking at this real quick. So when we look at the modulus, if this is my stress axis, and this is my strain axis, so we call this the strain, and this is stress. We're literally just graphing one versus the other. So for concrete, you have more strain than you do stress. So what you have is a low number, let's say like, what was that, 3 times 10 to the 6th, something like that. But steel, its slope was way up here. That was like 29 times 10 to the 6th. So what we have is a linear relationship here. The slope of that line is basically your modulus of elasticity. That's your E value. So notice E here is a lot lower. So my slope is lower because as strain is getting larger, stress is not. But what's happening is strain is getting larger, stress is getting a lot larger. So what we're noticing is a lot higher number, okay? And again, that's kind of what you're looking at when you're dealing with modulus of elasticity. So we might think because that slope is more that material is stronger. That doesn't necessarily imply that, but kind of we use that as a principle in general. So we're going to look at problem 8.7, and 8.7 gives you a concrete cylinder that has a 6-inch diameter. It's got an original length of 12 inches. Let me go ahead. We're going to draw this up. And I'm going to use a cross section, but your picture kind of shows it three-dimensionally. So if you're following along in the book, I'm just making it real generalized. Okay, so there's my concrete cylinder. It's going to have a load placed on it, and we're going to measure a couple of things. So let's do something here. This is distance from here to here, and then we're going to have an incremental change over here. Oop. Okay, we've got so let's see, we've got a standard 12-inch cylinder. So it's 12 inches this way. And they tell us that the diameter of this thing, if we look at that problem, is 6 inches. So it's a 6-inch diameter. So that would be, if we were looking at it in cross section, it's like 6 inches this way, but it's round in cross section, okay? They tell us that this thing has a small amount of deformation. So that deformation was measurable, but it's really small. That's 0.001 inch, okay? And because this is concrete, you know that the E, if you look in a chart, or he gives it to you actually, is 3 times 10 to the 6th PSI. Okay, so that's our amount. So we want to know what is the P, the amount of force that will cause deformation to be 0.001. So this is really cool now because in the last section we were just looking at, okay, we can calculate stress as long as we know P in the cross-sectional area. And we can calculate strain very effectively because we know the measured values. We get the original distance and we got the deformation. Okay, but now we're able to solve things like, well, what force is causing this? So let's list everything we got. This is concrete. We need P. We know that the deformation is that the original L value, original distance, is 12. That allows me to calculate a strain, right? We also know that the area is calculable. So let's go ahead and we're going to calculate that area. So we know that this is pi d squared over 4. So we have 5 times 6 squared divided by 4. And let's see what we come up with now. 6 squared times pi divided by 4. I get 28.3 inches squared. Okay, everybody okay with that? All right, so we want to, okay, so we want to solve P, which I didn't put on here. P is this. Obviously, it has to be in compression. Does everybody agree with that first off? That's got to be compression? Because this is what? This is necking down. It's getting smaller in that direction. Okay. All right, so here's what we know. Because we just saw that E is equal to stress divided by strain. Okay. But what's the definition of strain? Strain is delta divided by L, and the definition of stress is equal to force divided by cross-sectional area. So E can be stress over strain, but it can also be P divided by A divided by delta over L. If we clean that up a little bit algebraically, we're going to have PL, going to bring the L upstairs and bring the A downstairs. So E is now equal to force times length divided by delta. So it just went from this to this to this. And this is extraordinary right here because this allows me to solve for any of those variables that I need. If I have 1, 2, 3, 4 variables, I can solve for the fifth one. So in this case, what we want to solve for is this. Everybody see that? So I can now write this. I'm going to pull this out a little bit so we can see what's going on. So what we're saying is E is equal to PL over delta A. So we want to solve for P. So force is going to be equal to E times delta times A divided by L. Does everybody agree with that? Algebraically, I just brought these guys over that and I solved for P. Is that good? So now we can plug in numbers. We have E is 3 times 10 to the 6th times delta. Now you have to think about units too. I'm not putting units. Why don't I do that? Let me back this up. I'm going to go put my units in there so we can see what's going on with this. I'm going to erase this so I have a little bit more room, okay? So let me erase this out. Okay, so if I take and write this in terms of units, E is 3 times 10 to the 6th, whoops, and that would be pounds per inch squared. Now we know that delta is 0.001 inch, and A is 28.3 inches squared. And we're dividing that by length, which is 12 inches. Okay, so let's look at the units because we know that the P has to be in pounds. So if we notice here, inches cancel inch, inch squared cancels inch squared, and what we're left with is pounds. So when we do the math on this, let's see what we come up with. I came up with 7,075 pounds. So 7,075 pounds was required to force this. And now notice we were able to use this, which now gets material in that. Has everybody seen how that works?
Yeah.
Now, let's think about this logically. If we were using steel, okay, this number would be 29 times 10 to the 6th, okay? In order for this to give you a 0.001 deformation, this number would shoot way up, right? That would have to shoot way up because this is bringing more rigidity or more stiffness. So as that number gets bigger, this one would get bigger to have the same amount of deformation. this equation right here, being able to take this and then bring it into something like this and then do something like this is very, very important to strength of materials. So this interrelates stress to strain to modulus of elasticity. Okay. So this is a key equation to memorize. Modulus is your stress divided by your strain, and then also measure the definition or memorize the definition of stress, force divided by cross-sectional area, and strain, deformation divided by original. All right. How we doing on that? Okay, so far? You're going to have pretty many problems to take a look at. So a lot of them are going to be doing this kind of thing where you just, what you're really doing is just going to be taking these equations and manipulating them. But you really have to look at, units. And you think about it logically, I need to come out with force, so this has to come in force. That's why make sure these cancel properly. Okay, that's going to be really critical. And make sure they're in the same unit. So if this was in feet, and that was in inches, you're going to have to make sure that everything's working. You're going to have a unit mismatch. And we're going to look at a problem 8.8 now, and this one is metric, so we really got to watch the units on this one. Is everybody okay with this before I move on?
Yeah.
Okay, I'm going to go ahead. We're going to take a look at problem 8.8. So let me clear this up. So in this, if you look in your book, this is on page 258. And so what they have is a balcony that is suspended from 4 steel cables. And they have a load of 100 kilonewtons that are being applied. They want you to determine the diameter of a cable such that the deformation doesn't exceed 10 millimeters. So the cables are 5 millimeters long, they're steel, and we're going to assume that they all have the same diameter. So we're dealing with the same area, okay? Because you could have problems if they don't. All right, so let's see, I'm going to draw my balcony here. Here's my balcony. And I'm going to draw my ceiling. Well, I'm going to do my ceiling because I don't want to worry how big it is going to be. So I'm going to put my ceiling up here. This represents my ceiling. And this is the, oops, and then this is going to be this is going to tell me that distance. All right, so we got a cable here. We're going to assume they're equally spaced and however they're done. I got 2 on this side and 2 on this side. We know this distance. This is 5 meters. Now, one thing to keep in mind about this problem, it's going to be more about units than anything else. Okay, so you really want to watch units on this and watch me with this. So if you have questions, let me make sure you know what I'm doing. So this balcony is 100 kilonewton total load. Okay, it's 100 kilonewton total load. We know it's 5 meters. We know we have 4 cables. We know that the deflection or the deformation can be no more than 10 millimeters. So that's the maximum deflection that you're allowed in this problem. We need to come up with the diameter. Okay, so I think that's what we're looking for. Yeah, we want to look at the minimum diameter, okay, diameter min for a deflection max under that condition with that distance and that loading. Okay, so this is what we're solving for, that guy right there, all right? So we also know that this is steel, and steel E is given, this is given as 270,000 megapascals. So a megapascal, this is 10 to the 6th. So another way of writing that I'm going to do this now because I want to get this into a unit that's going to be commensurate with what I'm doing. That's 10 to the 6 pascals. Okay. We've really got to watch our units. And we could also call that, that's the same thing. Remember, a pascal would be a Newton per meter squared. Okay. Newton per meter squared. Okay, everybody okay with that? All right, so we need to solve the diameter. And so what we actually have to do is solve the area, essentially. So here's another thing. I can either solve the area total, which would be the area of that, plus the area of that, plus the area of that, plus the area of that. And then when I get done, I can divide that area by 4 because I'm looking at one cable. Or I can take the initial load and I can divide it by 4 because I'm going to say each one of those is going to carry a certain amount. So I'm going to do that. I'm going to take the force and I'm going to divide it by 4 so that what I'm getting is 25 kilonewtons per cable is what you're getting at, okay? That's per cable. Okay, everybody see what I did there? And so then when I solve the area, I'm going to be solving the area of just one cable instead of the total area, right? So we now know that the force is 25 kilonewtons, but that's the same thing as 25 times 10 to the third newtons. So we're going to get everything out when we get to that point. All right, so we have, if we go back and look at this equation, we know that the modulus of elasticity is stress divided by strain. And we further know that stress is force divided by cross-sectional area, and strain is deformation divided by L, which ultimately gives us PL over A delta. Okay, same thing that we just derived last time. So what we're actually trying to solve here is A, because A is related to this. So we can't solve diameter directly, but we can solve A. Knowing A, then we can solve diameter. So I want to rewrite this equation in terms of A. So what I have here is E is equal to PL over A delta. So rewriting that, we would have A is going to be equal to your force times your original length divided by delta E. Okay. And what this will do, this will give us, when everything's put in here, it'll give us what we need. So we can start plugging stuff in. Now notice, I want to make sure everything's in either meters, millimeters, and probably newtons. Okay, so I'm going to convert everything to newtons and meters. All right, so the first thing I want to do is we have 10 millimeters. How many meters would deformation be? So we've got 10 divided by 1,000, right? That will give us 0.01 meter. Okay, so this is in meters squared per Newton per meter squared. This is in meters. I need that in newtons, and that's already in newtons. So we're in good shape. So force is 25 kilonewtons. So kilo is 10 to the third. So that's the same thing as 25 times 10 to the third newtons. Length is 5 meters. So that's already in meters. We just converted this to meters, so that's going to be 0.01, and we're going to multiply that by 207,000 times 10 to the 6th. Okay, so remember this was in megapascals. Mega is 10 to the 6th. Okay, so that's where I got that from. So what we have now is everything's canceling. We're going to be left in meters squared when we do this. So let's see what we come up with. So we have 25 times 10 to the third. We're going to divide that by the bottom. And you can do the math. Let me know what you come up with. Here's what I come up with. 60.39 times 10 to the negative 6 meters squared. You guys check that and make sure that that's what we're coming up with. Anybody getting that number? Are we okay with that?
Just a second.
Okay. Just want to make sure. The biggest deal with this type of problem when you're dealing with metric is that you're dealing with these units, okay? And you got a lot of that to deal with. So I would suggest either getting everything in meters, that's probably your best bet. And then also make sure that you're dealing with probably straight newtons. Because what will happen is if you put this in as 25 and not 25 times 10 to the third, you're out by a factor of 10 to the third. And that's going to happen more often than not. So try to get everything to newtons and everything else to meters or meters squared. That's going to be your best bet. Unless, you know, if you're in millimeters for everything, that you can leave it at that as well. So just watch it, okay? You doing okay there?
Yeah.
Okay, so I want to convert this. This is where it gets a little tricky. I want to convert this to millimeters, okay? Because this number really is meaningless when I come into a meter. It's going to be a small rod. So how do you convert meters to millimeters? It's 1,000 times, right? So 1 meter is 1,000 millimeters, right? But when you're talking about area, what you're multiplying is, you have to square that number, okay? So we've got that times 1,000 squared. So what that does is gives us 60.39 millimeters. So that is the area of that rod. Okay, that's the area of the rod. So I'm gonna, now what I want to do is ultimately solve its diameter. So let me do this over here. Let me erase this here. Delete. Delete that. Okay, so to calculate now the area into diameter, we know that area is pi d squared over 4. But what we're actually after is d squared. So d squared is going to be equal to 4 times the area divided by pi. And if I take the square root of both sides, I end up with 4 times area divided by pi square root. So we get 4 times 60.39 divided by pi. Oops. And we're taking the square root of that mess. I'm running out of room. Let me move some stuff over here. So this then, when I do that math, the diameter that I'm looking for, 60 times 4 divided by pi square root. We're looking at a rod that has to have a minimum diameter of 8.77 millimeters. Okay. So in order for this balcony to work with 100 kilonewton load and not deflect any more than 10 millimeters total, we have to have a rod that is 8.77 millimeters, and that's also over a distance of 5 feet. Now, that means this is the minimum, okay? So you couldn't order a rod that is 8 millimeters. And if they're like standard rods that we get in Imperial, you probably don't have an 8.77 millimeter rod. So you could probably either get an 8 millimeter or a 10 millimeter. So I could go up to a 10 millimeter, it would be no problem. This is just the minimum. This is the minimum diameter, okay? That's your diameter minimum. All right? We wouldn't go, if we go less than that number, we're going to deflect more than we want to have happen. And then that's a problem, according to this problem, all right? Any questions on that, guys? I'm sure there are questions, but no questions so far? Okay. All right. Anybody out there?
Yeah, I mean, I have a few questions as the process goes on, but
Okay.
I'm just gonna wait till Thursday. And
Are you sure you don't want to tackle them now?
yeah,
Okay.
because I kind of want to focus on studying more for the tests, and then Thursday I'll have those for you.
Okay. Yeah, definitely. You're gonna be working on some of these problems, Jacob. So, you know, as you get into this, I think you'll see that it gets pretty simple. But you have to think more units now. Okay, you seeing that's real and critical.
That's what's
Yeah.
confusing me too.
Okay. Well, here's the one thing, Max. Imperials are a lot harder. Okay.
Yeah.
I'm sorry, I take that back. Metrics are a lot harder. Imperials are a lot simpler because you're usually working in just straight inches and PSI, okay?
Yeah.
So with that, that's not an issue. But when you're dealing with these sizes and you got mega and kilopat and all of that, you got to really keep focused on what you're doing. Otherwise, you'll get the right number here, but it'll be wrong by a factor of 10 to the third or wrong by a factor of 10 to the fifth. Of course, then it's wrong totally. But that's just a little bit more of an issue, okay? So it will, I promise you, it'll get a lot easier once you start doing it. And then it starts to make sense.
All right.
Yeah, but we're basically using 3 equations and we're just manipulating them to get what we need out of it, okay? There's
All
3
right.
key equations. And the key equation, I'll just do this real quick, okay? And this will just, hopefully this will kind of help. Key equations are this: stress. Stress is force divided by cross-sectional area. Strain is deformation divided by original length. And E is stress divided by strain, right? So from those 3, you can get literally anything you want, okay? Because if I replace in this equation stress with its definition, then I get P over A, and strain with its definition, deformation over L, right?
Right.
And then that can get cleaned up. That
So the middle one is deformation?
This is right here. This is deformation.
Oh.
Or that's deformation. that's little delta. I'm not doing a very good, that's really kind of more like that. Okay. Are you with me?
Yeah.
Okay. So it's stress here is force divided by, I just plug that in, right? And strain is just deformation over L. Strain is deformation per length, okay? So it's unitless. Deformation per metal length. Is we okay with that?
Yeah.
When I clean this up then, I get PL over A times, incremental deformation. So this gives me this equation, E is equal to PL over A delta. So from this equation, we write this guy out, you can pretty much get anything you ever want out of that. Because usually you know 4 of those, okay, kind of thing. If you only know 2 of those or 3 of those, then you got a problem, all right? So it just depends. You got to look at what you're given, and you got to look at how you can write it. And other than that, it's becomes pretty simple. So for instance, if I gave you stress directly and E, and I ask you to solve for the deformation, you knew original length, you'd be able to do it because you could plug that in, you could plug that in, and then you would be able to take this and rewrite it out and solve for deformation or original length. So it just depends on what you've got given, all right? Does that make sense now?
Okay. Yeah.
You'll see it the more you do it. You're just gonna have to do it a little bit, okay? What you're gonna do is start slow solving this kind of stuff, and then I think you'll have a couple of problems with this, and then once you introduce this, then you'll be doing this kind of stuff a lot and just rewriting it. I would try to be able to memorize that, and memorize that so that when you can come down here and write this any way that you want to. I wouldn't just necessarily memorize this equation because you don't necessarily know where it came from, okay? If you recognize that you've got this related to that, then you can write it any way you need to.
And that symbol that looks like a 6, did you say that was a stress?
Sigma, yeah, that's sigma. It really kind of looks more like that. Yeah.
Oh, okay.
I'm just drawing it really crappily, sorry.
Oh,
Yeah.
good.
Yeah, if I'm putting it in like this, it's not a 6, okay? So that's sigma. I believe that's a lowercase epsilon, and then that's a delta. That's a lowercase delta. Those are the symbols that are typically used. And then P is force, and then L is usually length, original length. So these two guys are distance, okay? That would be force, this guy would either be pounds or newtons. This would be either feet or inches or millimeters. Same thing with this guy, feet. Typically that's never gonna be in feet because it's a small number. If you got feet of change, you got a problem. So this one is typically unitless. It has no units, okay? And this one is gonna be in pounds per square inch, or kips per square inch, or it could be pascals, or Newton per meter squared, which is the definition of a Pascal. Okay.
All right.
Does that help?
Yeah.
I think also, let me look at the end of the chapter. He might actually, yeah, so you look at page 272, Tom shows you those exact direct things as I just did. Okay. And if it keeps it, he's got those key things right there. All right. But you're going to be doing this a lot. Okay. So you'll get the idea once we start working through a little bit more. Okay. Does that make sense now?
Yeah.
Okay. Perfect. All right. So let's go. If you're good with that, I'm going to go back to I want to talk about tension testing a little bit. Okay. So how does E become a value? How do we get that? Well, it's done experimentally. It's done through testing. Okay. And I think we talked about this. Just want to make sure. I'm pretty sure I talked about this, but let's see. Oh, no, this is getting into what we call the tension testing and stress and strain diagrams. So there exists a relationship between stress and strain for a given material, and we know that that's a fundamental thing of design now, as we saw. So it was basically assumed in what we were just talking about, that modulus of elasticity is a constant, and that's a linear slope of that line, essentially, is what it is. You can think of modulus of elasticity as the slope of the line, okay? And it's the relationship between stress and strain. So if you graph strain on the x-axis and stress on the y-axis, you know, where those two cross, that gives you a point. And all those points would be along that linear relationship. But the reality is that stress and strain don't give you a constant value along that. So in other words, materials aren't linear from the beginning of the load cycle until they rupture. They actually start to change. So what we get into is what we call a stress-strain relationship. And a common method to do this is to do what's called a tension test, a static tension test. So what they do is they take a specimen of a material. A lot of times they're using metals. And it's usually either a bar-shaped cross-section or it's usually a circular cross-section. And it's basically is like threaded rod. You have thread on the top and the bottom. And you have a certain fixed diameter in that material. That material is put into, you screw it into the top and bottom of an apparatus that'll then take and pull this apart. You have a device known as an extensometer that used to measure the deformation. So as that specimen is pulled, it's measuring how much that's elongating. And this specimen's pulled at a slow rate, and it's usually pulled from no load up until it fails. In other words, it'll pop. I'm going to put some, I got some videos that I'm going to show you, put up on the webpage for you to look at. But it's really simple. You just put that specimen in there, you turn it on, put the extensometer on it, and it measures the amount of load, and then it measures the amount of change in length before it pops. And then by doing that, you can take the loads and convert them to stress because you're dividing those by the cross section, and then you're measuring the strain directly, essentially, by that what they call an extensometer. And what you get is what's called a stress-strain diagram by plotting the stress values against the strain values. So basically, material scientists, they do this all the time, and that's where you come up with those numbers like 29 times 10 to the 6th or whatever. But remember, those only exist in what we call the linear range. So we'll take a look at that diagram here. If you look on page 261 of your textbook, there's kind of a brief diagram in there, and I've got one a little bit better that we'll take a look at. But there are a couple of important areas and or points that exist when you look at the tension stress-strain diagram. One is called the elastic range. Then we have what's called the proportional limit. So this range is a range of values where this is actually one fixed point. Then you have what's called a yield point, which is also a fixed point. Then you have what's called the plastic range and the ultimate strength. Let's look at this guy here. So this diagram I kind of redrew that shows that a little bit better. It's kind of that same picture. This is what is called an engineered or an idealized stress-strain diagram. The reality is that materials don't exactly do this, but this has kind of been generalized. So in this axis, what we're doing is measuring strain, or plotting strain, and we're plotting that against stress. And in this area, notice from zero load up to a point, this line is linear. And this slope of this line is actually your modulus of elasticity. So if you took the value here and divided it by the value here, basically you're getting a slope of that. So this is called the elastic range because what that means is if you take and you release the load on that particular specimen, it'll go back to its original shape. Okay, so in this area, as long as you load it anywhere from zero load up to this point of load or actually strain, when I release it, it's going to go back. And that generates this point called the proportional limit, which actually is a little bit higher, I believe, than the actual linear. So it's actually starting to curve a little bit at that point. So what you get to then is a point called the yield point. And I've got it kind of at the peak of this curve, but it's not always the peak. But what's happening here is that the strain is increasing a lot, but the stress notice is not changing much. So in this area, this is called your yield range or yield point. This is your yield area. And then at this point, what's happening is what's called strain hardening. So as the material is being pulled more and more, notice stress is actually increasing. And you'll get to a peak here, which is called your ultimate tensile stress. What's happening here is the atoms are starting to rearrange in this area, and they're actually getting stronger. The material is getting stronger, but there's other things that have happened to it. It will not go back to its original shape. And that's why if you notice, once we get past the elastic range down here, we get to what's called plastic range or plastic deformation. That means it's like plastic, you pull it out, but it won't go back. And in here, what's happening, it's starting to do what's called necking. So what that means is the material, you actually can visibly see the cross sections getting smaller and smaller and smaller until you actually pull it apart and it pops or it ruptures. So the engineers, we don't really want to know a lot about this up here because this doesn't work for us. So you try to engineer a part down in this area, and we really usually keep it in the elastic range. The absolute last point we would ever design to would be a yield stress up in here. Okay, so let's look at these different areas. We're going to talk a little bit more about this probably next week as well. So the elastic range, that's that region in the diagram that extends from that point of origin to what's called the elastic limit. And that's the area where the range of the material, remember, will return to its original length once the load is removed. And in this area, that range is truly linear. And that's where we get the number of the modulus of elasticity. So it is based on this linear, this is your modulus of elasticity, just the slope of that line. And in this area, this is the area where when we remove the load, it goes back to its original shape. Proportional limit, that's the point where the line on the diagram starts to curve and where the relationship between stress and strain is no longer linear. So we've just increased it a little bit. It does start to curve. I think you actually are still considered in the elastic range at that point, but it's no longer linear once you get to that point. The yield point, that's the point on the diagram where the strain begins to drastically increase, but there's not a big change in stress. And this is where the material begins to stretch uncontrollably, so it gets into that plastic range, plastic behavior. This is the yield point, is usually the point that's considered the highest point you would ever design to. Now, what it does mean is that it can stretch uncontrollably, but it still gives us a little bit of time. If a structure is starting to fail and you haven't passed the yield point, you still have time to basically deal with that structure a little bit, but we can't design to that point. Yield points, by the way, we'll talk about those a little bit. There's different ways of defining them. It's not truly, like I said, that high point. Sometimes they use offsets. They use different offsets and they intersect the offsets with that graph. I'll talk about that a little bit. Probably won't do it this week, but we'll talk a little bit more about that next week. Then the plastic range, that's the region to that right of that elastic. And that's the point where the level of stress just causes permanent deformation. So that whole, basically, if we go back to that chart here, this whole area is plastic in this area. So from this point on, it's just uncontrollably stretching if you're putting it in tension, and it's never gonna go back to its original shape. So the last point that would be really anything you would consider as your ultimate tensile strength, that's the highest point on the diagram. So that's the highest stress level that it can actually exceed. And once you hit that, then not too long after that, you'll hit what's called failure or rupture, where the part actually breaks apart. So when they do these tension tests, they actually take those specimens and they pull them apart until they fail. So like, it's pretty interesting to do it with steel or aluminum, those kind of things. You also get different fracture patterns, which are really specific to the type of material. Some materials are brittle, some materials are what we call ductile. We'll be talking about that a little bit more next week. And we do have one of these. If you look on page 260, that's called a Tenius-Olson testing machine. We actually have one of those down in the old wing, but it's sitting there and we can't get in there anymore. So we would normally do a tension test so you can actually see this. But like I said, I'll provide some videos for you so that you can kind of see this thing. Okay, so the last thing I want to talk about today is what's called Poisson's ratio. And Poisson's ratio, it's not something that's used too often, but it was developed by Poisson, who was a French, I believe he was a French scientist in probably, I think, the 1800s. And we talked about the fact that when you load a member axially, it deforms or it strains, but it also induces it in two directions. So the deformation in the axial direction, it's either elongation due to tension or it's shortening due to compression. But what actually happens in the transverse direction, it also reverses that process. So for any material, your volume is going to remain constant essentially. But if it strains in a lateral direction or axial direction, then it also strains in a lateral direction. So, and I'll show you a picture what I'm talking about here in a sec. So tension in an axial or primary direction is going to result in a shortening in the lateral. So if you're putting a part in tension axially, it's expanding or elongating in the axial direction. But because the volume's staying the same, it's going to shorten in the lateral direction. And compression is going to do the reverse. If you compress the axial or primary axis, it's going to elongate in the lateral direction. Let me show you exactly. See a picture of this, exactly what I'm talking about. Let's grab this real quick. So, oops, I started something else there. Let me clear this up. Okay, so here's what we're saying. If we have a part like this, and let's say we are pulling on it. If we pull on it with a force in this direction. So that's my axial direction. That's my longest direction. That's where we're going to experience the most deformation. So what's going to happen to this? It's going to elongate, okay? So it's going to get longer this way, but notice because it's also elongating and volume is staying the same, it's getting smaller in this direction. So this is your, what we call this is your axial direction. This is your axial direction or your primary direction. And this is your lateral direction. So that's, notice, in tension, because this is a tension force, that's tension. This cylinder started out originally that way, so it elongated, but it's compressing this way because the volume's staying the same. If we're looking at compression, compression is going to be something similar. If I'm pushing on that material with a force this way and a force this way, so this is a compressive force. Now what's happened to that? It's getting shorter in the primary direction, but it's elongating due to the volume. Okay, that's all Poisson's ratio is dealing with, or saying, which should make sense to you. You can see that. Take a marshmallow and just squeeze it, and you'll see it puff out on the sides. That's an easy way to see this process. So Poisson basically said he could take those two and he could develop a ratio. So if you took the lateral strain and divided it by the primary strain, you'll get this ratio, which is Poisson's ratio, and that's the Greek symbol mu. So what you're getting is that unitless constant because strain is in units of inch per inch or millimeter per millimeter or meter per meter, and you're dividing that by the same unit. It's just a unitless number. Okay, we don't use this too much in design, but it allows you to say, hey, if I got so much deformation in this direction, I could predict what the deformation is in another direction. That's all it's really used for. So it's not a very, very commonly used thing. Here's some values that you would see. Oh, that's wrong. I should not say. I edited this. So this should be values of Poisson's ratio, not E. So the values of Poisson's ratio, I need to fix that slide. Sorry, guys. The Poisson's ratio can be found in your table 2. These are published values. And you can see some of the similar ones there for mu. Notice they're unitless. Steel's 0.25. Copper is 0.35, aluminum. Again, those are probably more averaged values. Notice concrete has some varying values there from 0.15 to 0.25. So let's look at an example here real quick. And then I think Max had a question or two maybe that we can solve for the chapter 7. Okay, let me find what I wanted to look at. A real quick example here. I had this all together. Let's see if we can find that real quick. Ooh. Sorry about that, guys. I got too many things floating around. Okay, here's an example we're going to do for Poisson's ratio. Pretty simple. Flip over to this. You won't use Poisson's ratio too much, so don't get too caught up on it. It's really pretty simple, actually. But let's do a new diagram here. We'll just do a real quick example of that. I think there's a couple of problems. Okay. So we've got a cylindrical steel block. So we're just gonna, let me just draw a block here, and it's a cylindrical, so it's a cylinder. So it's got a 2-inch diameter. This thing is initially loaded with a compressive load. So we're gonna have a compressive load on this cylinder, like this. So that cylinder has a compressive load of 40,000 pounds. And it is going to have a lateral or a primary strain. This is your primary strain. That's measured to be 0.000.00, 12. That would be inches per inch. And your lateral strain is 0.0004. So that would be inch per inch and inch per inch. Now, how these things are measured, they can use what's called a strain gauge to determine that. So they clip this material, they clip a strain gauge on there and measure it. So we can measure it in 2 directions. So what we want to do is find Poisson's ratio and also modulus of elasticity for this material. Also keep in mind this specimen is a 2-inch diameter. Okay, so D is 2 inches. All right, so we're going to solve, we want to solve first Poisson's ratio, and then we want to solve what the E value is for this. Okay, so Poisson's ratio is really simple. The Poisson's ratio mu is your lateral divided by your primary. Okay, so that gives me 0.0004 divided by 0.0012. And if you do the math, let's see what we come up with here. So we get a number of, let's see, that's a unitless number. So what does that do for us? Well, for one thing, it tells us that we might be able to determine what kind of material this is, even though we don't know the material, because if we looked at that chart, and if we see a number that we came up with there on that chart might show us a value there. So if you notice, aluminum in that chart is 0.33. So this is possibly an aluminum specimen. So even if you didn't know that, you might be able to solve that, okay? All right, so this is pretty straightforward. So now the larger issue is solving this E. All right, so let's take a look at this. E is defined as what? Stress divided by strain, correct? And we can solve stress, right? Because stress is force divided by cross-sectional area. So in this case, the force is 40,000 pounds. The area is pi d squared over 4. 2 squared is 4, so that's just basically 40,000 divided by pi. So let's see what we come up with. Yeah. We get like 12,000, 125,000, 663. Oops. That would be pounds per square inch. Does everybody agree with my stress value?
Yeah, that's what I got.
Okay, so this we can solve directly, can't we? So stress is 125, 663.7. Now we're going to divide this by strain. Which strain do we use here? Does anybody know? Because that's important. We need to use the strain that's in the axial direction. That's happening this way. So that would be what we call the primary strain. You almost really hardly never talk about lateral strain because look how small it is. It usually doesn't really even mean anything. So when we solve this, let's see what we come up with. I basically get 10, 4, 7, 20, something like that, and that would be PSI. So you could display that as 10.4 or 10.5 rather, times 10 to the 1, 2, 3, 4. Is that right? Oh, wait a minute. Let's see. Let me check something real quick here, guys. I'm getting a different number here. I may need to check this. Yeah, I get a different number for this here.
I got like 127,000 something.
Yeah, I did too, Max. I'm going to change that now for this number, right?
Yeah.
Okay. You get 127. Let's see. Let me check that. Sorry about that. I must have, again, my calculator. 12,732. Is that right?
Yeah, I
Okay.
think so.
So, all right.
Yeah,
Sorry.
that's what I got.
Okay. I think I had some, again, my calculator is just not doing me very good today. So let me check into that. Sorry about that. Well, you can see this is real time. Okay, so let me erase over here. Doesn't help when we're trying to define this stuff and then I make mistakes. So that means this is wrong too, right? Get rid of that. Get rid of that. Get rid of that. All right, so this should be better number. 12,732.4. Okay, so let's divide that and let's see what happens now. It's like 10,000 or 10,610 basically PSI. Is that right? Oh, no. I'm missing decimal places. It's 329, right? Call that 330. How's that? Much better? So it's 10,610, 330 psi, which we could define as 1, 2, 3, 4, 5, 6. So we could call that 10 times 6, 10 6 to the 6th psi. And I think if you look that chart up, you'll probably see that's about what aluminum is. So it makes sense that Poisson's ratio is going to be material specific, and as is the modulus of elasticity. And these two really, if you look at the chart for modulus, this really much agrees, that very much agrees with aluminum, so does that. So if we were trying to determine what this specimen was, we could say, yeah, that's probably aluminum. Okay, is everybody okay with that? We're not going to do a bunch with Poisson's ratio. I think there's two problems that we might get into. Other than that, I don't think that we're going to have an issue. Okay. You guys want to take Max, you want to take a look at that problem? I think we have time to do one or two of those problems out of chapter.
Sure.
Okay, just make sure, I think I'm done with everything here that I want to get rid of. Yeah, okay. So I do have a few typos on that, but I need to fix that. But let me go ahead and go back to here. You said problem 3 out of chapter 7, is that right?
Yeah.
Okay. All right. And then if we have time, then maybe we can do the other one too. All right. So so we're shifting gears here. We're gonna go back to chapter 7, and we will have time, by the way, on before the test. So, all right. So we're looking for what are we looking for in this problem? We want to calculate the moment of inertia about the centroid XX and YY axis of this shape, right?
Mm-hmm.
So basically, this is a simple problem because, let me see if I don't know how well I'm going to be able to draw this. I don't think I can really, dang it. That's what I was afraid of. I don't think there's a way, probably is a way to copy this thing, but oh, there we go. That's not too good. Let me see if I can get that a little bit better. Basically, we have a ring. That's not probably about as good as it's going to get, guys. Okay. We have an inside diameter of 5.5. So the inside diameter and the outside diameter is 6.0. Okay, so if we're looking at centroidal axis on this, let's say you put an axis point down here, or an origin initially. Let's say you had say you had an origin initially down here in this area. Okay, is everybody okay with what I've done there?
Yeah.
So what's the X-bar distance? Wouldn't this be just 3? Because it's a circle. To the centroid, that's to the centroid of this shape. You agree with that?
Yeah.
And wouldn't this also be 3? So this
Okay.
is my YY axis, and this is my X axis. So I really don't even need to go through any kind of part for that. Are you okay with me doing that?
Yeah.
Okay. So to get the moment of inertia, what do we do? Shape, I, area, right?
Yeah.
Then we have what? D, AD squared. And this would be, let's see, This is going to be going from shape to shape, right?
hmm
Okay. And then we have
It's like IX total or something.
IX total. Yeah, thank you. All right, so let's call the outside shape, shape 1, and the inside shape, shape 2, and recognize that that's going to have a negative or voided, okay?
Yeah.
All right, so let's do the area real quick. Area for that diameter is going to be pi d squared over 4, right? So we have pi times 6 squared divided by 4. I get 28. Is that 2827? Is that right? For the area, outside shape?
The area of
The area. Pi d squared over 4?
hold on, what did I do?
Okay, well, maybe you did moment of inertia. We need that too. I did area first.
Okay, 28. Yeah, that's what I got.
Okay.
28.27.
All right, so for the shape moment of inertia, if you go back to chart 7.1 on page 218, notice for the moment of inertia, it's just pi r to the 4th times, or divided by 4. Okay, so we have 6 to the 4th times pi divided by 4. You guys check this. My calculator doesn't do that really easily, so I just want to see. I got 1017.888. Verify that for me, will you? That's what I'm getting. Oh, you know what? What did I do? I did diameter. Sorry, my answer is wrong. Let me check something. So it's pi r to the 4th divided by 4. So that's going to be 3 instead of 4. I used 4, so I had a wrong value. Sorry about that. So my number was a lot greater than it should have been. 8. How 63.62 sound? Is everybody
Looks
getting
good.
that? Okay, all right. I was using diameter before, so I was wrong by a huge factor. All right, so what is the d distance? That would be the x-axis centroidal axis of the composite shape as compared to the x-axis axis of this outside shape, and that's going to be what? Aren't they sitting right on top of each other?
Yeah, so wouldn't it just be 3 or 0? I don't know. I'm confused with.
It's 0 because the axis of this shape is sitting on the axis of the composite shape.
Oh, I see. Yeah. I
Okay,
get it.
so 0 times that squared just gives me 0, and this just becomes what? 63.62, right?
Yep.
All right, so the area of that other circle, that's a void circle. So that's going to be, let's do the area first. 5.5, is it? Yeah, it's 5.5. 5.5 squared times pi divided by 4. So this should be a negative 23, looks like 76 maybe. And the moment of inertia on that is going to be pi r to the fourth divided by 4. So 5.5 divided by 2 to the fourth. You guys verify my number. I get a negative 4492. And it's negative because it's a voided area, right?
Yeah.
Okay. So did you get that same number?
Yeah.
Okay, so this is going to be also 0 now because it's the axis of this guy and the axis of the composite. They're sitting on the same point. That's that. This just comes over as that. When you sum these, you get 18.7 inches to the fourth, and that's your IXX. Okay.
Yeah.
That one's pretty simple. Now what's going to happen in the Y? So now you're looking at it this way. This is exactly the same thing. Area is not going to change. And because it doesn't matter on a circle whether you look at it this way or this way, it's going to have the same moment of inertia. So this will also be your IYY value. Now you could go through the chart and determine that, but it should come up to the 18.7 in both directions.
All right.
Does that help, Max?
Yeah.
Yeah, that one was pretty simple. Okay. So you want to look at 7 or at least get started on it? Or 5? Yeah, 7. Was it 7?
Yeah, we can do it.
Okay. Let me clear this guy. At least I can get you started, and we could always finish it if we don't have time, okay? All right,
Yeah,
I'm
that's fine.
gonna try to, now this one we have to solve the moment of inertia, or the centroidal axis first, so that's gonna be a little bit, dang it. Dang it. Trying to make that look as representative as I can. Okay, and I'm gonna go ahead and take out. So really what we have is this part that looks like this, but we want 2 parts, right? So did you have a way you define those 2 parts? There's actually probably 2 ways to do this. You could look at one big rectangle and then one small rectangle, or 2 little ones. Did you have a way you wanted to look at that?
I just did 1 and 2 for
Okay.
both of the rectangles.
Which one did you call this, like one rectangle this way or one this way?
I did 1 from the top to bottom, and then the 2 from left to right.
So you're saying like this?
Yeah.
Okay, so you're calling that like right there one shape and that another shape?
Yeah.
Okay, so we'll call this shape 1 and shape 2. How's that sound? And we know this is 4 inches and this is 4 inches, top to bottom, left to right. And this is what, 0.75 and 0.75. Agree?
Yeah.
Okay, so we got to do our centroid first. We're going to go ahead and call this the origin just to keep it simple. So we're going to have shape, and we're going to have what, area, x value, ax, and then y and ay. Okay, so we have 2 shapes, shape 1, shape 2. The area of shape 1 is going to be 0.75 times 4. It gives me 3. What'd you have for the x value? It should just be what? Half of the 0.75?
So 2 or point.
0.375?
Yeah.
0.375 times 3. 1.125. What about y?
2.
2. 2 times 3,
6.
6. Okay, so now we have, for the second shape, we have what? 4 minus 0.75, 3.25 times 0.75, 2.43, 2.438, I guess we'll call it. So the centroid of this, it's going to be 3.25 divided by 2, because this distance is 3.25, right?
Yeah.
So half of that, 3.25 divided by 2, and then we have to add to that the 0.75. So that gives us the distance to his centroid is that right? What'd you get?
For x,
Yeah.
I got 2.375.
Okay. Okay, so we're going to multiply that by area. Okay, and what about the y value?
0.375.
Okay. Times the area. .914.
Mm-hmm.
Okay, so we sum and we sum and we sum. Check my numbers. You agreeing with this?
Yeah.
Okay, so X bar .272 and Y bar should be the same. They're just basically, there's a little rounding going on in there. Essentially, they should be the same. I'm just going to call it to 2 decimal places, okay?
Yeah.
So they should be the same because we've got symmetry going on here, right?
Yeah.
Okay, but you okay with those numbers?
Yeah.
Did you have those before by any chance? Or
I'll be honest, I didn't actually do this problem, but I did want to look at it though.
okay. So
Right.
does that make sense though that we got now?
Yeah, that makes a lot.
So if I put, let's see, this is the XX, X bar. What we notice about this shape, which is pretty common, is that the actual centroid, the balance point's outside of the shape. Okay, that happens. Remember, we talked about that. So
Yeah.
let me move this now. And like I said, you should recognize that because this is asymmetry, those numbers have to be the same. So because they're not, it's just rounding. That's all.
Mhm.
You did you recognize that?
Yeah,
Okay.
they looked about the same.
Yeah, and they are. So, okay, so this is your XX. This is your YY. And this is 1.27 inches, and that would be 1.27 inches. Okay? All right. Can you take it from here?
Yeah.
Okay. Why don't you see if you can finish it, and then we'll take a look at that. We can take a look at that first thing on Thursday.
Okay.
So anybody else questions? Let's we can wrap this up, and then we can answer some more. I'll answer some more questions on Thursday, and then we'll be looking at that test. Like I said, I don't think it should take you very long. It'll be 2 problems. One will be a centroid. One will be a moment of inertia. Make sure you know how to use the charts, because you may have to deal with an engineered type shape. Okay. Any questions in?
Nope.
Okay, I'm gonna stop the recording, and then I'll get this guy formatted and out there for